I'm the very last speaker of the conference, so thank you very much for sticking around until the end. Appreciate that. So I also want to join the other speaker in thanking the organizers for this beautiful conference. I enjoyed it a lot. I learned a lot, so we already applaud, but thank you very much for this. I will present some work that I did in collaboration with Victor Godet and Amartya Singh last summer, and some work in progress with Filiberto Ares, Pasquale Calabrese, Michele Fossati, Amartya Singh, and Marco Venuti. The last three are great students that are either applying now or that will apply in the fall, so that in mind. And since I'm the last speaker, I will break some traditions. So the paper didn't appear last night. I will not present the figure with the 3 cycles. And also I will not present the picture of the symmetry TFT, the club sandwich, or other type of food. But there will be some connection with ice cream. So let's see. Okay, so more seriously, what I want to talk about is symmetry breaking, and in particular, how we can detect and measure symmetry breaking. So, of course, the standard approach is to use local order parameters, local operators that can get a VEV. This is the standard Landau paradigm, and so whenever a local order parameter has a one-point function, then we detect that the symmetry is broken. However, in the last few years, Ares, Morciano, and Calabrese proposed a different type of observable, similar ideas that appeared from other groups before. This is a quantum information-based approach. It's an observable that I will define. It's called entanglement asymmetry. It's built on the theory of entanglement, on quantum information. And this quantity is nice because it is positive if and only if the symmetry is broken. So it is a faithful detector, a faithful measure of symmetry breaking. Besides, it depends on a subsystem, so it measures whether there is symmetry breaking in a subsystem, and so in particular, it depends on the choice of this subsystem. It gives us more degrees of freedom, and so it contains more information than local order parameters. So it is based on entanglement entropy. So this is an observable that measures how much degrees of freedom in some subsystem are entangled with the rest of the system. The rest I will call B, the subsystem is A. And so in quantum mechanics, the standard definition is that if we assume that the Hilbert space factorizes into 2 parts, we take some state that could be pure or mixed, is the same. Then we construct the reduced density matrix by tracing over the complement of the subsystem. This gives us rho A, and then we compute the von Neumann entropy. Now in the following, I will just call rho this reduced density matrix instead of calling it rho A. And now this definition, with many caveats, can be extended to quantum field theory. Some regularization is necessary. We already heard about it from Hitchell's choice talk a few days ago. And in quantum field theory, typically the subsystem is some spatial region, of course, although other things can be considered. So now, suppose that we have a system with some symmetry, and in the first part of the talk, I will consider the case of U1, and then in the second part of the talk, I will go to more general symmetries. So we assume that the charge can be also factorized, or can be broken into 2 parts, one that acts on the subsystem and one piece that acts on the rest. Then the symmetry is broken in the subsystem if and only if the reduced density matrix does not commute with the charge. So the question is, how can we quantify or measure this condition? And so the idea of Ares, Morciano, and Calabrese is the following. We take the density matrix, we construct a projected density matrix. So in particular, we project on a sector, so the Hilbert space will break into sectors of different charges, and for each sector we do a projection, and then we sum over all the sectors. So in practice, what this does is that the density matrix will be made of blocks, that depends on the various charges, and we keep the elements along the diagonal, and we throw away everything which is outside of the diagonal. And this can be rewritten in the following way. Is essentially an average over the action of the group. So here alpha is an element of U1, and this is how the group, the U1 acts on the density matrix. So once we have the original reduced density matrix and the projected matrix, we want to measure somehow the difference, and what was proposed by those people, and they call it entanglement asymmetry, is essentially to take the difference of the entanglement entropies, and with a few steps you can see that it can be rewritten in the following form, and this goes under the name of relative entropy. So why this is a good measure of symmetry breaking? Because by using standard property of this relative entropy, it is semi-positive definite, and besides it is equal to 0 if and only if rho is equal to rho q, and so if and only if rho commutes with the charge. So it is a faithful measure of symmetry breaking. If you want, this is in contrast with an order parameter that it might happen that for the particular order parameter that you pick, even though you break the symmetry, that particular order parameter does not get a VEV. Of course, if it gets a VEV, you know that symmetry is broken, but the opposite is not always true. Now, notice that in this construction, I only use the state. I never mentioned the Hamiltonian. And so in particular, this construction can be used both for spontaneous as well as explicit symmetry breaking. So we are not using the Hamiltonian here. Finally, I say that in entanglement entropy in quantum field theory there are in general divergences. However, this is a difference of two entanglement entropies. And so if the symmetry is broken spontaneously, or explicitly but softly, let's say with some relevant operator in such a way that it's not broken in the UV, then we expect the divergences to cancel in quantum field theory, and so generically, under this condition, in general, the relative entropy does not suffer from divergences. Okay, now this quantity is difficult to compute because there is a logarithm of a density matrix, so there is another quantity which is easier to compute. This is called the Rényi asymmetry, and here you compute the trace of some integer power of the density matrix and the projected one, and so this is much easier to compute. However, it turns out that this also shares these nice properties. It is semi-positive definite, and it is 0 if and only if the two matrices are the same, and so in fact this one can be used as well. And if you do analytic continuation in this index n and you take the limit n to 1, that you can recover or if you want, define the entanglement asymmetry. Yes?
So for the case of spontaneous symmetry breaking, is it a specific case of A that would detect spontaneous symmetry breaking? So for the usual spontaneous symmetry breaking, is there a choice of region A that would detect spontaneous symmetry breaking? What should I...
Well, if you break the symmetry homogeneously, any region A will detect, you would expect that it detects the symmetry. Of course, depending on the size or the shape of this region, you might detect a different amount of symmetry breaking. However, there might be situations in which the symmetry is only broken in the complement of the subsystem, and then this quantity here will not detect it. So this will detect symmetry breaking within the region. And in quantum field theory, it's difficult to construct such a situation, but in a spin chain you can do that. So you can construct a state that only breaks the symmetry outside of the subsystem, and then this quantity will not be detected. But this is a feature somehow, because...
So in a spin chain, do you consider finite one or infinite spin chain?
You can take a finite one, a quantum mechanical system of just size.
So symmetry breaking is like 0, 0 plus 1, 1. Is that a state that we could call it symmetry breaking?
Well, you need, so a state breaks the symmetry if it does not commute with the charge. So it should not be a state of definite charge. It should be a state with, in which the charge is not well defined. Okay. And so that will be a state that breaks the symmetry. All right, so this quantity has been, since it was introduced, has been studied by various groups, in particular the group of Calabrese, in a variety of situations, in various spin chains, integrable system, quantum circuits, and various systems. What I want to talk about is in CFT. This is related to my work. So if you want to study a CFT, the vacuum does not break a symmetry. And so if we want to compute something which is non-trivially interesting, we need to consider some excited state. And of course, I mean, there is an infinite number of excited states, so you have to make a choice. And we decided to choose states that are created by a scalar primary of charge 1 and some dimension delta. And because of what I just explained, you cannot just construct the state with the primary, because this will be a state which is an eigenstate of the charge, so this will not break the symmetry. You need to create a state that doesn't have a definite charge, so you have to take, for instance, the identity plus the primary, okay, or something else. But the primary is not enough. Moreover, you see here there is a parameter, so in this first part of the talk I will consider the limit in which this parameter is very small, so I will compute this asymmetry in some in a perturbative limit scheme, just at leading order. Okay? Now, these states have a nice Euclidean preparation, so you can prepare them in Euclidean, with an Euclidean path integral. Essentially, in the Euclidean past, you put your operator at some point, this creates the state, and then, if you want to create a density matrix, you need the specular situation in the Euclidean future, so this will prepare the dual state, and then in order to compute the reduced density matrix, you need to glue the spacetime on the complement of the subsystem, and then you are left with a cut along the subsystem. So this is an Euclidean path integral preparation of your density matrix. Now, in order to compute a symmetry, we need to compute this projected density matrix, and then take the power n and the trace. And this also can be done in the path integral formulation. So essentially, it turns out that rho q to the n can be written in the following way. So this is called a charge moment. You alternate rho, the reduced density matrix, the action of the group, rho, the action of the group. Here there are parameters, and then you have to integrate over these parameters. However, there is a constraint that the sum of the parameters is 0 modulo 2 pi. In other words, you make insertions of operators such that the product is the identity. Okay? This is just a rewriting of the definition. And now, how do you compute this trace? Well, there are various ways. Let me just describe one for the sake of time, which is the replica method. This is quite standard. Essentially, you have to create a geometry in which you take n copies of this Euclidean path integral construction that I had. There was a cut. I take n copies, one on top of each other, and then I glue through the cut from one copy to the next. And then the last one is glued with the first one. Now, this allows you to compute rho to the n. If you want to compute this rho q to the n, on top of that, along the cuts, when you go from one copy to the other one, you have to put a topological operator that implements the action of the symmetry. So these are the standard topological symmetry defects. And so in this way, you construct some spacetime that in general has curvature singularities along the entanglement surface that also contains these topological operators. In my case, also contains local operators that are used to create the state, and you're supposed to compute the partition function on this geometry. Now, in general, this is very difficult, in particular because there are curvature singularities. In 2 dimensions, the situation is better, because if we take a single interval, there is a conformal map to just the complex plane. And so with this conformal map, essentially you map your problem to the complex plane and various insertions. You also have these topological operators. What you have to do is to move them and collapse them on top of each other, because as I told you, they multiply to the identity. And at the end of the day, in this perturbative approach, so leading order in lambda, you are left with a bunch of 2-point functions that you have to compute and sum. So these are 2-point functions. And then higher order will be 4-point function, and so on and so forth. So this computes the Rényi asymmetry. If you want the Rényi entropy, you should analytically continue this number n to the complex and take the limit. Okay? And this can be done. I'm not going to show you the answer computed in this way, because in fact it turns out that there is an alternative way that, because of the sake of time, I don't have time to explain, uses the fact that this is also a relative entropy. At the leading order in lambda, we can expand this relative entropy. At the end of the day, one is able to obtain an integral formula that is valid not just in 2 dimensions, but in any dimension. And okay, so this is the expression. This is the first order in lambda. essentially, this is an integral of analytically continuous two-point functions. So you can recognize here, there is, again, a continuation of the sign, and there is the delta, and this is integrated. So essentially, this is an integral of two-point functions. It has the same origin, although it's derived in a different way. Now, this integral, in fact, can be performed, if you want, in terms of hypergeometric functions, and so the message is that this quantity can be computed. Now, this formula here is the particular case of what I call the Rindler geometry, so this is a semi-infinite line. However, then you can use conformal transformation to map the semi-infinite line, or in general dimension a half plane, to other regions. And so you can obtain the result in other situations. For instance, you can obtain spherical disks in flat space. You can obtain a spherical disk in finite volume, on a sphere. And you can also do positive temperature, but the space becomes hyperbolic plane, with the exception of two dimensions where it is just a line. So one can obtain this quantity, and I could show you some plots, but first I want to discuss another thing. So it turns out that one can also compute temporal evolution. What do I mean by that? So with this Euclidean preparation, we prepare a state, okay? We can think of this as a quench, and then we can let the system evolve with the Hamiltonian. The Hamiltonian will preserve the symmetry. And we can ask question, what is the time evolution of this asymmetry? How do we compute this? Well, with the same trick. Essentially, we have to move this cut along Euclidean time. Now, this configuration is no longer specular, so this would compute a non-Hermitian density matrix, but then you do analytic continuation, you go to Lorentzian time, then the cut moves vertically, and this computes the time evolution of this asymmetry. So, what do we want to see from here? Well, we have these excited states, the system evolves, so this excited state will break the symmetry, we expect, so there should be some asymmetry. Then we let it evolve, and since we are looking at a subsystem, we expect that this relaxes, and so we should see that the asymmetry reduces, goes to zero, and the symmetry should be recovered. Of course, this is an effect of the fact that we look at a subsystem, because suppose that we are in finite volume, if you have an excited state, it's not going to go to the vacuum, but as long as we look at the subsystem, it will look like the system relaxes, okay? Okay, I will show you the plot in a second, but in fact, this is an out of equilibrium process, and so different states might relax at different times, at different speeds, and we could explore the possibility that states in which the symmetry is broken more, in fact, restore faster the symmetry. And so this is what we obtain. So this is the asymmetry that we use as a quantification of how much we break the symmetry. This is time. Different curves correspond to different states that are produced with the operators of a different dimension. And indeed, if you follow a curve, at the beginning the symmetry is broken, but then the system relaxes. It looks like we recover the symmetry. However, you see that states that break the symmetry more recover the symmetry faster, okay? And so this is a sort of quantum version of the Mpemba effect. I don't know if you heard about this effect, but essentially this is the effect that warm or hot water freezes faster than cold water. Okay? This very unintuitive phenomenon cannot happen adiabatically, it has to be out of equilibrium, but it is a true effect. It was observed by Aristotle long ago, and then it was somehow rediscovered and investigated by a kid, African kid called Mpemba, and if you ask me later, I can tell you the story. Okay, so this effect was observed first by these people in a spin chain. It has been observed in a variety of systems, and here we see that it also happens in generic CFT in generic dimensions. Okay, so now in the remaining maybe 10 minutes or maybe less, yes.
Just to be sure, so sorry, the plot is for 2 dimensions?
No, this is generic. In fact, the formula does not, so let's go back to the formula, does not depend on the space-time dimension.
But the delta will be below the unitarity bound. You have 0.25?
Yes, okay. Yes.
This is in 2 dimensions, but the expectation is that the same qualitative behavior happens for higher
Yes,
dimensions?
so of course, so the formal is the same in any dimension. Now, which operator are acceptable depend on the space and
So you don't see
dimension.
any special features at the unitarity band?
No. So let me notice that this is a perturbative expansion. This is just the leading term.
Oh,
there
the
are
plot is
various
from the leading
things
term,
that, so yes. So already, so if you look at the behavior at large system sizes, you can observe that this approximation breaks down. So it's possible that also for late time there are breaks down and so on. I mean, it's possible there are some effects that are not captured by this leading approximation.
Okay.
Yes.
Can I ask a question?
Yes.
Oh, yeah. So here the plot, it seems like most of the curve are passing through the same point, more or less. Is there?
Yeah.
Or is just a coincidence?
Yeah, I don't know. I think it is a coincidence.
Okay.
So this is a very special system. More general system have been studied, for instance, an integrable system by the group of Calabrese. And I think that there you can play more, essentially constructing more complicated excited states. I think that you can engineer different behaviors. So I think that here is just a coincidence.
So does it also depend on the charge of the state? If you have like very large charge, would it like relax faster?
Yes, I think that there will be a dependence on the charge, but essentially will appear some scaling way. So I don't know on top of my mind what is the dependence. But of course, in this leading term, the formula is so simple that the dependence is very simple.
I see.
Okay. Now, yes, in the second part, I would like to tell you how to generalize this construction to more general symmetries. So before going to non-invertible symmetries, let me tell you what happens with invertible symmetries. So abelian symmetries the asymmetry can be defined in the very same way, because so you have one-dimensional representations, so you can just construct these projectors and sum over the projectors. This once again keeps the elements of the density matrix along the diagonal and throw away what is outside. And you can rewrite it as an average over the group. Now, if you go to non-abelian invertible symmetries, this formula is wrong, does not work. Why is that? Because you have higher dimensional representations, and if you take a block of some given representation, you have in the density matrix the representation and the conjugate. This contains a singlet, but also contains other stuff, and so you have to project to the singlet. Essentially, in each block, you have to keep just the identity matrix in each block. And so this formula doesn't work. The correct formula is this one. You have to average over the group, and this essentially selects all the singlets in the density matrix. However, now you see, if you want to generalize to a non-invertible symmetry, it's not obvious how to generalize it, because this formula is not going to work, and it's not completely obvious what it is, this average over the group. So we investigated this question in 2 dimensions. Okay, so we have some symmetry fusion category. The most basic data is given by the fusion algebra. And let me first discuss the case of the full system. So we put the system on a circle. There is no subsystem. Then this fusion algebra is the algebra of line operators that act on the Hilbert space of the circle. So these L are the topological line operators. And essentially the goal here, in order to define a symmetry, is to construct a symmetrizer, which is some linear projector that takes the reduced density matrix. It produces a symmetrized density matrix. This should be trace preserving, because we want this one to also be a density matrix. It should obviously commute with the symmetry. If the original matrix is already commuting, then this projector should not do anything. And then in principle you can ask more. For instance, this projected density matrix should be positive, and should be Hermitian, and so on and so forth. But in fact, it turns out that if you already impose these 2 conditions, so let's say that you use some bootstrap approach. So you say, okay, this symmetrizer will be obtained by acting with the lines with some matrix here, and you impose trace preserving and commuting, you obtain some linear equations. These are simple enough to solve, so this is the general solution. And you see that this is a formula that only depends on the fusion coefficients. So you can plug this formula here, and this construct this symmetrizer. And so if you want, this is the equivalent of the average over the group. Now, this formula is not very illuminating if you look at it. So let me just unpack a little bit. So if you consider a commutative algebra, for instance, if you have rational conformal field theory, then this formula is just the sum over the one-dimensional representations. All the representations are one-dimensional. They are described, so these representations are described by some unitary S matrix. You can construct the projectors, and you can check that this formula reproduces what I had before. If you have a non-commutative algebra, it's a little bit more complicated because now you have higher dimensional representations. You can still construct the projectors, but then you can check that our formula is not just the sum of our projectors, but it has a further projection to the identity matrix in each block. Okay? And one example that we studied was the Hager-Up fusion category, because essentially here you want to find fusion algebra or a fusion category which is both non-invertible and non-abelian. So you have to look for some specific examples. Okay, however, it turns out that you can do better, because in fact non-invertible symmetries not only act on the untwisted Hilbert space, but they also can map twisted to untwisted sectors. And if you want to do that, you can introduce a total Hilbert space in which you put together all the twisted sectors, and then the non-invertible symmetries allow you to define the so-called tube algebra, in which on the circle, if you want on these cylinders, you have twisted sectors that are given by this vertical line. The red line are the action of the topological operators, and they can change one twisted sector into another. And they form an algebra because you can put one on top of the other, and then you can resolve using various F moves this product and obtain another fusion algebra. Okay? And this time you see that the coefficient of the fusion algebra contain more information about the symmetry, because that depends on the F symbols. So this, for instance, should know something about anomalies. Now the tube algebra is non-abelian, but okay, we can construct the symmetrizer precisely in the same way that we did before. And it turns out that this is more powerful than the fusion ring. How much time, sorry, do I have? 5 minutes, okay. So let me just show in what sense this is more powerful. So let's take the Ising model. So suppose we just look at the Z2 spin flip symmetry, the invertible one. Then the identity and the energy operator are neutral, so we are not going to detect them. The spin operator is an eigenstate, so if you only use the spin operator, you are not going to break the symmetry. You need to do some combination like the identity plus a sigma or epsilon plus sigma. Okay, so this state will be detected. Now let's go to the fusion algebra, the Z2 Tambara-Yamagami symmetry. Now epsilon, the energy operator, becomes an eigenstate because it's odd under Kramers-Vanier, but you cannot use it alone once again, but 1 plus epsilon would break the symmetry. But now if you go to the tube algebra, it turns out that the spin operator is in a two-dimensional representation with the disorder operator, and so now even if you use just the spin operator alone, not 1 plus, this is enough. I mean, this can be detected because this breaks the symmetry from the point of view of the tube algebra. And so this will be detected by the asymmetry constructed with the full tube algebra. Okay? All right, there are various things that one can discuss, but let me skip that. So for instance, before I discussed the CFTs, one can discuss spontaneous symmetry breaking if you deform the CFT with some RG flow. But let me jump to the case of the subsystem. So now we want to study the case in which there is a subsystem. Now, as we already heard in Hichiol's talk, in principle, there are divergences at the entangling surface. Each term in the definition of the asymmetry, which is an entanglement entropy, has divergences. We need to regularize this entangling surface, and one way is to remove a small disk, impose boundary conditions, but now this means that the natural action of the symmetry will be on an interval with boundary conditions. And so the natural object to use is the strip algebra that was also introduced in various talks. So what is the strip algebra? Essentially, you have boundary condition, you have your line operators. Now, in general, these line operators will have some decoration at the end, will depend on extra variables. And once again, you can construct an algebra out of them because you can put one on top of each other and you can fuse them using the various moves and they give you some fusion algebra. Now, of course, it would make sense to use symmetric boundary conditions, right? Because this is some regularization that you have to do. So it would be natural to use a regularization that respects the symmetries. However, this is not always available. So sometimes there are symmetric boundary conditions available, sometimes there are not. And in fact, in the invertible case, the case of symmetry breaking boundaries has been studied, for instance, by these people. So in our work so far, we only looked at symmetric boundaries. And what happens in this case is that essentially you can repeat the construction. You can construct this symmetrizer with this bootstrap approach, and you can define your asymmetry, and then you can compute it. Now, it turns out that there is also a more algebraic approach that one can use. In particular, for instance, for the strip algebra, this is a Hopf algebra, and so one can use a coproduct to give a more algebraic and more explicit definition of this symmetrizer, which, however, turns out to be the same as this bootstrap approach. Okay, so let me just give you one example. This will be essentially my last slide. So let's consider two copies of the Ising model. Why two copies? Because we want to find this strongly symmetric boundary condition. So there is a sub-algebra, symmetry subcategory, which is Z2 times Z2 Tambara Yamagami. The lines are the spin flip on one side, spin flip on the other side, but then there is only the diagonal of Kramers-Vanier. Now it turns out that this one here admits a strongly symmetric boundary condition. You can construct your strip algebra, H8, and then, okay, this is non-abelian. You can repeat the construction, you obtain your symmetrizer, and for instance, here I'm showing the result of the asymmetry, this time as a function of the system size. And the particular state we consider is the identity plus here is the energy operator on one of the two sides. And essentially what detects this state here is precisely the Kramers-Vanier, right? Because this is odd. So here, for instance, you see the dependence on the system size. When the size is very small, you don't detect the symmetry breaking. Yes.
Which one of the four TY-Z2-Z2s is it?
Say again?
I mean, there were four Tambara Yamagami Z2-Z2 categories. Which one is it?
Yes, this one, yeah, you have to select some...
Okay.
Yes, I mean, H8 is the strip algebra, and the... Okay, if this answers the question. All right, so yeah, so you see, but the system size is very small. There is no symmetry breaking because this is the symmetry breaking in the subsystem. When it goes very large, now you see this is no longer the approximation of lambda small. By the way, this is the second Rényi asymmetry, is not the entanglement asymmetry. This contains also the 4-point function, and this changes this behavior, so it goes to a constant, and this constant is log 2, which is precisely corresponds to the fact that when you act with the symmetry, this changes sign, and so there are two states. Is one plus epsilon and one minus epsilon. So you get a log 2 from the asymmetry. Okay, so let me conclude. Okay, I'm not going to repeat what I explained, so let me conclude with some open questions that I think that are interesting. So I described zero-form symmetries, non-invertible zero-form symmetries. Of course, it will be very interesting to generalize to higher-form symmetries. I expected in this case, for instance, the shape, the topology of the subsystem will play a more important or major role. It will be interesting to investigate better the role of anomalies. In what I described, anomalies were not really appearing. It's not clear to me whether they are supposed to appear or not, so I think that this is an interesting question to investigate. And then there is a whole connection with holography. I didn't describe this, but of course for string theorists, this is an interesting an interesting question. And in particular, once one connects with holography, can ask whether there are connections with black hole physics, for instance, the physics of charged black holes, and whether this quantity could be interesting for some describing some physical phenomena. Okay, thank you.
In the context of spontaneous symmetry breaking,
Yes.
Is there a way to use this quantity to prove Merlin-Wagner-Coleman theorem?
Yeah, I don't know. It's not so. I briefly thought about it. Okay, I don't have any smart idea. Let's see that is, in some sense, this measures how much the symmetry is broken in a state. So I'm not sure that this could give you a theorem that the symmetry cannot be broken, in the sense that, I mean, I expect that the result would just be that since you are not able to construct in infinite volume a state that will break a ground state that will break the symmetry, in some sense, you cannot detect it, but you see this quantity doesn't know whether the state that you construct is a ground state or is an excited state, because it does not depend on the Hamiltonian. So I suspect no, but okay, I don't want to close the door. But
can I ask a quick second question? So you have a slide on the Ising model where you compare 3 different algebra.
Yes.
So in the second case, doesn't sigma also break the symmetry?
No, right? Because in the fusion algebra, sigma is mapped to 0. So it is, if you have the state created by sigma, that is mapped to 0. So if you are in the tube algebra, sigma is mapped to mu, right, but mu is in a twisted sector. So if you just work you just put your lines around and you just collapse the line without an attached external line, you just get 0.
Map the state to a different state. That's what it means by breaking it.
Yes, exactly. So as long as the state is an eigenstate, it's not enough to break the symmetry. Because when you take, in the density matrix, the phases cancel out. You really need to map a state to another one. That is symmetry breaking. Yes.
Can you construct similar quantity that can detect strong two-weak symmetry breaking?
Can detect what?
Strong two-weak symmetry breaking for density matrix.
Strong two-weak?
Yeah, so strong symmetry is like if you add the density matrix with the unity operator, then you get a phase multiplied by the density matrix. So that's strong symmetry. And the weak symmetry is that the density matrix commute the symmetry generator. So far, the symmetry discussed is weak symmetry.
Yes.
Yeah. So I was wondering whether there's some similar quantity, similar to the entanglement symmetry that can detect strong symmetry breaking or strong two-weak symmetry breaking.
Yeah, I don't know. I haven't thought about it, but.
I have a quick second question.
Yeah, sure.
So in the definition of the Rényi symmetry, do you assume QA has integer spectrum? Yeah, can you have a situation where QA and QA bar both are fractional, but there is some with integer? Yeah,
so in this, let's see, in the formula that I showed, I was assuming, when you write as a sum over projectors, I was assuming that there is an integer spectrum, and the fact that you write it as an average over the group.
But the sort of reduced charge to a region does not have to be integer, that can be fractional. As long as the sum, inside outside region is integer, then it's okay. This is the symmetry fractionalization situation.
Yeah.
But then if you allow fractional spectrum, then the definition of the Rényi symmetry will have some problem. If you go to the factor format, there will be some periodicity issue.
Yeah, the fact that, so in the first part, I was giving the sloppy definitions of the various objects, because what you really, already when you start, you say that the Hilbert space factorizes in quantum theory is not true, and then you assume that the charge breaks into the sum of 2 parts. That is also not true in general. So what you really have to do, right, is to have a map from your Hilbert space to a factorized Hilbert space, which, for instance, you can do with this removing the circle, and then you want to know how the symmetry acts on the subsystem once you have defined it properly. And then at that point, okay, you have the symmetry, it acts how it acts.
Do you allow the action to be projective?
Well, okay, I mean, this has to do with the question of anomalies. Yes, I mean, I would say you do allow it to act projectively. Now, whether this has some subtleties that requires you to change the construction of this symmetrizer is what I think should be investigated. So I only consider the case in which there are the strongly symmetric boundary conditions. If you have some projective actions that interpret some anomaly, there will be some problem with the boundary conditions. And then the question is, what is the effect on the computation?
Okay, thank you.
Yeah. Well. Go ahead.
Okay, right. So maybe I can quickly comment on Paul Shen's question. So indeed, actually, people have used like similar relative entropy to detect a strong weak SSB. So when I was looking at the slide that rings a lot of bell, I have not completely connected dot yet, but something similar has been discussed. Yeah, right. So about my question, so suppose I drive a continuous phase transition of the SSB, right? So that a relative entropy should have some singularity, should have some kind of critical scaling, something like that.
Yeah, I think so. I have no idea what is the behavior.
Yeah. So which exponent should it correspond to? It correspond to any of the known exponents?
I don't know. It's a great question. I don't know.
Okay.
I don't know, but this, I mean, this has not been. Let's see. As far as I'm aware, it has not been explored even in, spin chains or simple systems. Yeah, it's a great question.
Okay.
Yeah, let me just say one thing, that, I mean, this quantity is a close cousin of the symmetry resolved entanglement entropy that the people also discussed. I don't know if this is what you had in mind. Oh, okay.
Can you elaborate more on the holographic description of this thing? I mean, in the case of the invertible symmetry, I would assume or expect that there should be some bulk charge associated with your asymmetry, I guess.
Yeah.
At least in the continuum case, if I have a U1, right, and then I can build the dual current in the bulk. Yes, and in the non-invertible case, what is the gauge thing in the space?
Yeah,
I mean, how to build the charge?
Non-invertible case, which holographically, it's either impossible or it's going to be a mess. But I mean, in the case of U1, so it's a great question. So, is there a holographic description of this? I don't have the answer. I've been thinking about it. In this perturbative limit, in which you perturb the ground state in an infinitesimal way, then there is a holographic description that we explored. Essentially, you change your boundary conditions, and these give you the preparation of the state. In that case, yes, it is, you have to integrate something in the entanglement wedge. It's something weird, though. So it's something that is called canonical energy. You can rewrite it as a sort of integral of the charge in the entanglement wedge, but it's a derivative of that integral with respect to moving the boundary condition with modular flow. So it's something very strange, and I have no idea how to generalize it beyond this perturbative limit. So even the U1, I mean, I share the feeling with you, it should be something that has to do with the charge, but how to make it precise, I don't know.
Also, only at the leading order is like the canonical.
Just the leading order, yeah. What I described only computes the leading order.
I see, okay, thanks.
So in the H8 Hopf algebra example, can you also see the quantum Mpemba effect?
Quantum?
Mpemba effect.
I've not explored it. Yeah, possibly, I don't know. I mean, we did this computation a few days ago, so I mean, we have not explored Bayes operators and so on, but yeah, it's a great question.
Any more questions? Good. Thanks, Francesco, again. Thanks so much.